All, let us welcome our colleague Dr. Ambit Kumar Pany, Associate Professor for Department, and today he is going to speak on Galerkin mixed finite element method for partial differential equations. And let me say about Dr. Pany to all of you. He joined ITER in 2016 as assistant professor. Now he is the associate professor of our department. Earlier, he had experience from C.V. Raman College of Engineering as lecturer for 1.5 years, and then assistant professor at Gandhi Institute for Technological Advancement, Bhubaneswar. For almost 9 years, he was there, and he has a teaching experience of 17 years. He has earned his PhD from Ravenshaw University in 2017. His research interest includes computational partial differential equation, numerical analysis, and scientific computing. In particular, finite element methods for partial differential equation, etc. He has research experience of 2 years from Universidade Federal do Paraná, Curitiba, Brazil. Dr. Pany has fought in several national and international conferences and workshops, presented papers there. Dr. Pany organized a national workshop, Computational Methods in Science and Engineering at C.V. Raman College of Engineering, and an international conference, Numerical Analysis and Differential Equation with applications in 2019 at our university, that is Siksha, Anusandhan, University. So, Dr. Pany, once again, now you can start your talk of today on today's topic. Thank you.
Yeah, thank you, ma'am, very much, and thank you, Abhijit, for this opportunity. He gave me this opportunity that I have to speak something here. Let me think. With a short span of time, we are trying to arrange this seminar, or you can say this presentation. Initially, I was planning to go for a direct paper view or paper presentation. Things are with me, but as last few days we are going this hectic situation, I cannot prepare my slides. Then I change that. I will start I go for a very general stuff that I will start with finite element method. Then I will go to the mixed finite element method. Then I will talk about H1 Galerkin finite element method with a very layman way that everyone can understand at least the major facts or the cream of the methods. And if someone can pursue, we can start think to work on these areas. Okay, ma'am. So let me share the slide and how to share the slide. Just a minute. Yeah, this thing is here. So I think everyone can see the screen.
Yes, it is visible.
Okay. So my topic is H1 Galerkin finite element method for parabolic problem. The fact is that I'm thinking about the partial differential equations, but partial differential equation you can see for PDX we have lot of options. It is, we can say, it is elliptic, parabolic, and hyperbolic. But the fact is that if you think about the parabolic and elliptic, there belongs to one block, because if I take Laplacian u equal to f, which is a Poisson's equation, or you can say Laplacian u equal to 0, it is called elliptic equation. And if you think about the parabolic part, you just think about ut minus Laplacian equal to 0. That is called parabolic equation. So the basic idea behind, we are trying to explore this solutions of this type of problem, that this elliptic equation and this, you can say, parabolic equation. The fact is that some knowledge we can take from this equation and throw it here. So that is in this numerical world to explore the things. What is the some knowledge you can pick? Suppose if in a standard framework, if all of you know numerical analysis, when you're trying to solve the problem, you're using the difference scheme. In case of difference scheme, what we're going to do, we have to crack this problem by discretize the domain, whether in 1 dimension or 2 dimension, doesn't matter. We have to, if I have the, we have to convert the domain. If in R2, we can say that these are the grid, and in each grid, we are trying to find the solution. So by taking the suitable conditions, whether it is the initial conditions or the boundary conditions, basically for the boundary condition, that is important, because I have to, if I know the boundary, then from the use of this boundaries, I can evaluate the interior loads. So the concept is that enter the numerical things, numerical methods, we can say, it will be based on numerical method. We can say we have to discretize the domain and evaluate approximation solution, and on grid. So this is the entire story. Once you evaluate the approximation solution in the grid, then what are going to do? We have to, the next task is that we are going for interpolation, because we can think about the interpolation. Yeah, this is the first time I'm using this Wacom, so there is a little bad letters, but try to think about the concept. Once you get interpolate the things, you can recover the solution. So you can say recover the solution. So this is the exact thing happening in case of numerical method. If you are adopting any type of method for solving PDs, the first advantage you can get, if I think about FDM versus FEM, the advantage you can get, that is FDM you can think about a regular domain. Regular in the sense you can say that either I can take a square domain, I can take, in this case I can take, because the grids we can think in a square case. But if I go for an irregular domain, in that case we have the difficulties. That means if I take a triangle, in that case I cannot adopt FDM, because if I convert to grids, you can see that in a grid system we can find out that some points they are not comes under the triangle, or much more points it cannot be covered by the small, even if you take the smaller grid. So for that, to accomplish this concept, what is the advantage you can get? If I will be change the grid style, that means for the quadrilateral too, if I change it to triangle, then we can get a better result. That means if you have any type of domain, doesn't matter if it's triangle, then convert it to triangles, so that you can think you can cover the interior part very nicely. Suppose if you have star set domain, even in that case also you can say the finite difference scheme cannot be think of the solution, or you cannot approximate the approximation solution. Even you can get, but that is pure case. But here we can deal with this problem using finite element with the triangulation. So that's why major people working on this finite element method. Now the question is that when you think about this finite element method, again we can focus on two things, because I think much more people, I think 1 or 2 guys in our department or some people maybe know about the finite element method, but all people may not be aware about the finite element method. There is major difference between method and analysis. So usually the engineers apply this. This is the task of engineers. So that means whenever you can say that they have very complicated domain, there apply this method, conclude the things. But our perception is different. We are looking for the analysis part. So for this analysis part, what I'm going to do, we have to think the behavior, nature, existence, uniqueness, all this property of the solution. That's why analysis is a very, you can say, interesting, because lot of things are there which we can deal by this finite element analysis, or we can recover that means you can say by doing we can adopt lot of stuffs which is very new to us, but once you apply all these stuffs, you can enjoy the stuffs. So let's come to focus on the finite element analysis. So I will start with the analysis, because method that you can how to discretize, how to think about the functions, how to construct, that is a different issue. But you have to focus on the analysis, how we can calculate the things. So in finite element analysis, sorry, yeah. So you can say in finite element analysis, initially it will be started from the concept of Galerkin. So what Galerkin imposed? Galerkin imposed that if I start with a very simple problem, that is Laplacian of equal to f, and if I'm thinking about the solution, how the solution is supposed to be look like. In this case, there are issues. Solution. So if you think about the solution of this chart, it is always depend upon this chart. What? This is why this is happening. Now you can think, if I talk about this equation with a boundary condition that u equal to 0 on the boundary, suddenly you can feel that I have this equation something like this. That means you can take a draw where you can say the boundary is fixed, so there is no movement in the boundary, and if I'm adopting force F here, then I have to check what are the vibrations happening in the field. So that is that you give me that information. That means you can say in 2 dimension you can say uxy, in 1 dimension you can say ux. So the question is here, whatever F it might be, when I hit a drum, it is never continuous. It is never continuous. That means due to this touch, in a mathematical sense, where I can assume anything for this F, but when I'm going to a physical sense, I have the issues that F is not continuous. If F is not continuous, then how could I deal with this term, that double derivative of u? That means I'm looking for a u which double derivative is supposed to be equal to this term. So for that, people are trying to analyze in a different sense, because this finite element comes from the physical world directly. Because the civil engineers in early 1960s, they are started the finite element concept. Then later on in 1980s or 70s, people are thinking about this finite element analysis. So the question is that what type of F I can choose and where I can choose this U. So the solution completely depend upon the F. So for this concept, you can say that when people thinking about to develop the concept of finite element analysis, they are saying let F is continuous or discontinuous, doesn't matter. But if we can think about some function which derivative equal to continuous or discontinuous, then we can deal this kind of problem. For continuity, there is no problem. You can choose u as C1. That's fine. You can say it is continuous. The derivative is continuous. If you choose u belongs to C2, you can say it is continuous. Its double derivative is also continuous. But for the discontinuous fact, I cannot choose u in C2. For that, we have to develop certain theory which can be deal with the discontinuity. So for that concept, people introduce weak derivative. So weak derivative is very interesting fact in sense of functionals. So I'm not going much more about that. This weak derivative says that I can deal with the discontinuity, but that is subject to if it has a jump. Some finite discontinuities also we can deal. So corresponding to that, they develop the space That space is known as SOAWAL space. So in our first lecture, professor from NIT, he was started about this SOAWAL space, but I'm not going much more about it. So the thing is that here you can say that our priority is that when I'm trying to solve this problem, value equal to f, we are trying to focus that how we can think of the solution in sense of continuity, in sense of discontinuity. That is the first priority. Now, once people develop this classical weak derivative, or you can say SOAWAL space, they think it is easier. Now they're trying to think one more fact. If you think about this case in strong sense, you can say that I require u in C2. But if I can minimize this derivative, this order, is it possible or not? That is certainly possible by this approach. So that is, you can say that if I take del u equal to, suppose let's say this is equal to f, we can minimize this by this way. Let's say I just multiply with a smooth function phi in both hand side. Now you can see if I take phi is a c infinity 0 function, that forget about that symbol. That c infinity means you can think this is continuously differentiable. Whatever time you can take the derivative doesn't matter. Now, what if I do the integration? You can say that there is something happen. So what is this? What are the things happen? The thing is that we can say that one derivative will be thrown to this side. Now just think about the integration by parts. Now think in this way. If I take u double x, integrate with some function phi and upon 0, 1, let's say. So in that case, you can say this is the inner product. So you can think in this way, u xx phi upon dx upon 0 to 1. In that context, you can say that this is my first function, this is my first function, this is my second function. So in that case, you can say phi upon boundary. Oh, sorry. So we can express in this way. So we can see that how to write down the things. We can say this is phi integration of uxx. So we can write down ux. This is upon the boundary 0, 1 minus derivative of phi 1 integration, that is ux dx. So now we can say that if I have sufficient information about phi, that's why I'm putting 0 here. 0 means we can consider that it is compact support with the boundary. That means it will be 0 on the boundary. In that case, you can say this term is going to vanish due to this phi. Now that means instead of this case integration, we can write down that is nothing else phi x ux dx. So this is the idea. Now we can say that you can try to derive this using of the integration by parts, and I am adapting this phi belongs to C0 infinity. We can say this is grad u grad phi integration over omega. Then we have a term like grad u dot eta upon phi so this is become dx. This is on the boundary, that is equal to f phi. Now what actually happened? Now the question is that when I'm trying to express in this sense, now you can see that if I have more information u upon boundary, that means in this problem if I'm using u equal to 0 on the boundary, then in that case what's happened? And I'm choosing phi equal to u. In that case, what's happened? This term is going to be 0. That means basically I'm getting grad u, grad phi, grad u, that is equal to, or you can say grad v upon d omega. This is upon omega equal to f into phi. So we are getting a form like this. So when I'm getting a form like this, we can say this is the variational formulation. So whenever I'm trying to apply finite element method for particular problem, simply just multiply phi with the entire problem and find out the variational formulation. That means In operator sense, I can say this is AUV equal to FV. That's it. And where is the V? The V we can choose. V belongs to a vector space. Or you can say more, let's go for the more refinement. We can say this is a, that I'm looking for a V that is a Hilbert space. So we can ignore a lot of stuffs. Now, this is the form you can say. So if I get this form, every time, whatever the equation you can pick, you can convert it to this form, that is weak formulation. You can say this is UV equal to LV. Now, the objective, the Galerkin says that we can say under this weak derivative, under this, that means you can say under this Galerkin procedure, we are not looking for the C2. Here we can get the solution. That means you can say the single derivative is here. We can think U in C1, it will be satisfied. That means it will be satisfied this equation and I get the solution. So that means that is the first thing introduced by Galerkin, that he reduced the derivative. That's why this method is particularly interesting when we use loss regularity. That means if I have the domain, this space is not C2, I can even deal with the problem. So that is the beauty of this Galerkin method. So when I shifted this information to a finite element method, what are we going to do? Our concept is something like this. The concept is that my V, what is the, you can say that is the Hilbert space. We know that Hilbert space is infinite. So as it is infinite, when I'm trying to work in a grid point, I have to think a finite set. So when you think about the finite set, what I'm going to do, I cannot deal with the infinite case. So I have to think about a subspace VH, which is a subspace of B. And this VH, it is nothing else. We can take some points or some grid point. So, and this grid point, comes from the how you can take out your domain, or how you can say this grid you can derive as for the elements. So that is the concept of finite element. That means once I have the weak solution, we can convert this weak solution to, that means I can say that is UH VH, that is equal to L of VH, what is your F, or you can say this is F of VH. That is happening in case of finite element space. Finite element space. So now we understood that if I have a problem, that how we can transfer a problem from classical sense to a weaker sense. We know that how to get the variable formulation, and we know that how to define the problem in the finite element space. Now the next question is that existence and uniqueness. So what is the guarantee that when I did some weaker form, or we can say this is, we can say this is weak form. There is no form. This is called weak form, and my UH, that is, we can say that is the approximation solution. So the question is that how could you think that this solution is justifying in a strong sense? So for that we have to think about existence and uniqueness of the problem. So for this existence, you can say that and milligram, they justify that if I have this bilinear form, that this bilinear form, it is mapping from, you can say V cross B to R. In that case, we can say, if I say that AUV, if it is bounded, that means you could take the bound, if it will be bounded by the non U in the space V and V in the space V with some constant C. And the second part is that this is called, this particular condition is called bounded condition. So this is called, this is bounded, and the correctivity condition. The second condition is that AUV, or you can say, if I choose, this is AVV, both the terms are the same. If I say that this is greater than to alpha 0 B square, then this is called the correctivity condition. The interesting fact is that if you combine this, you can find an interesting result. Now you can say that if you take AVV, you can say this is less than 2, some constant into V in V square. This is the contribution from this, and this is gives you that this chap is greater than 2 alpha 0 V square. This is in space V. That means you can say one side you have infimum, another side you have supremum. So this is some way give the in-sup condition. So in-sup condition means people saying this is LBB conditions. So this condition means you can say that you are getting a stable saddle point. So that is the rootedness of this condition. That means if I prove this much, then I can say this problem has a solution exists, and the uniqueness it is derived from the U0. So that you can think of the uniqueness of the problem. That means we can say it is satisfy the Hara-Hara theory. So if I'm taking an elliptic equation, I can satisfy with this stuff. But if you think about the parabolic equation, we have a different scenario. So here, this is the requirement. So you have to prove this case, you have to prove this. That is, give the complete information about the existence and uniqueness of the solution. Then you have to think about error analysis. So in case of error analysis, we can think that we have two solutions. We assume that U is the continuous solution. So you can take as Galerkin. Then UH, you can take as FM solution. Then you take the difference U minus UH. So in the classical theory of finite element method, we have a very interesting result. This comes from Riesz representation theorem, that we get a minimum information. That is, we can say that CH introduce the result that we can say U minus UH, that is less than equal to. So that is a very interesting thing. Infimum over C times infimum over chi minus VH. Chi belongs to the space VH, such that this is U minus chi on V. That means you can find out that I can find a member in my discrete space that U minus UH, it is always less than to this member, that I can get this choice. So in that case, you can say you could take the discretized method. Now that is clearly indicate that this result depend upon your discrete points. So later on you can derive that it will be nothing else. This will be CH. You can say U in space V. That is, we can say it is on VH. So here if you think about the solution, that we can get the error in this form. But people then later on think about define a very nice setup. That means instead of this V, how they think about the space V, and they rectify this storage. So for that context, now they focus on the space. So for this space, you can say usually this to the space V, which is called H1. If at the boundary condition 0, I can say it is H1 0. I am not even go detail on this H1 0. This is that as rather than taking f is continuity, doesn't matter. We can take f is integrable function. So we can say we can say f is in L2 function, so that the derivative of f in L2. So that means you can say derivative of f that is in L2. So why I'm not write down L prime, I'm just write down df, because that is understood that this derivative we can say in a weaker sense. Weaker sense means I'm not using the strong derivative. And we have f equal to 0 on the boundary. F on boundary will be 0. So this is the basic concept. There are a lot of other stuffs are there, but still we can ignore. So we can say that space I can say H1 0, that f in L2, its first derivative in L2. If as we can see that we have only this term grad U grad V, that is equal to f into grad V. So that is indicate that I'm very happy. I can get the solution if I'm taking in H1. If someone looking for the solution in H2, he can take the things that he can go for H2. H2 means you can say that all the double derivative in L2. That is the difference between H1 and H2. So I think all of you get less or more idea. because you don't know about the SOAWAL space, so I'm not focused much more about the things. So the thing is that when I'm trying to solve Laplacian equal to f, our focus on either two space. One is H1, another is H2. But when I'm getting the solution in H1, then why should I be looking for H2? So I can go for H10 as u equal to 0 on the boundary. So we just focus on H10. Now, if I take H10, in that case, you can say, if I say that V belongs to H10, in that case, if I take U minus UH, the difference, the error estimate, you can say this square equal to CH V in H1. Or you can say this V in, if I say this B subset of H10, I can say this is in B. That means this is not a better result. But because this is showing the order of convergence of the error, that means how the solution converges to a exact solution. So then people thinking about to improvise this thing, that means that rather than taking V on H1, they are taking it is H10 intersection H2. So they are adding, they are putting some more regularity. So when they are putting more regularity, in that case, you can say that I can get U minus UH, that is less than equal to CH square V in H2. So which indicate that we are getting a better result. That means our solution converges faster. So this is the entire story. That means our main goal is that we are trying to play with H10, H1, and H1 intersection H10 intersection H2. So we are just focusing on these three space and try to think of the solution. Now come to the parabolic problem. So for the parabolic problem, if you minutely observe what exactly happened, this is ut minus Laplacian u equal to f. As I told, you can again say u equal to 0 on the boundary. Just think about a weak form. So if you think about the weak form, what are you going to do? Simply take multiply ut with phi. Phi is a function in C infinity. Then minus Laplacian u of f. That is equal to f into phi. So now if I replace phi equal to u, that means this is happening. You can say that which space you can think. Suppose if f is in L2, Laplacian of u, that means you can say u in H2, so you can consider u belongs to H10. This is sufficient because this Laplacian transport to gradient. So we can consider u equal to H10. Now if you replace phi by u, you can get this is ut u minus Laplacian u, that is equal to f into u. So now apply the integration by parts through the integration. So okay, so I'm not doing any integration on this part because the derivative is involved here. So what I'm going to do, I just take the integration on this side and integration on this side. Then if I rearrange the things, you can see that we can get this is del by del t u square. This chap is grad u square. You take the integration, even the same thing. That is equal to f into u. So this inner product. Now, here this problem is the bilinear system is looked differently. If I take, I can say this is AUV and this is my LV. So this is the bilinear form. We can say we can get the variational form that AUV equal to LV. But in this case, we have a different issue. That means if I apply the integration by parts, so this is over omega, this is over omega, this is over omega. So we can get a form like this. So when I got a form like this, now you can say this is a time-dependent problem. So this is a time-dependent problem. What exactly happened? We don't require Lax milligram theorem here. Lax milligram is not required. Not required. Because here, as it is time-dependent, we very sincerely you can say I can apply simply if I have the information u0, that means u at time 0. If I have this information, we know any derivative. That means if I try to convert this to a system of algebraic equation, system of algebraic differential equation, that means if I convert it to only first order differential equation, then I can apply Picard's theorem to conclude the solution. So you can say, you can think about the Picard's theorem. So that's why parabolic problem is easy to deal in the analysis sense. You can apply Picard's theorem to conclude the things. So if I apply the Picard's theorem, so how to think of this case? So for this case, as I told, that we collect some information from the Laplacian and throw it here. So from that, we can take the eigenvalues of this case. We can say, if I take this pi equal to 0, and I'm trying to solve this operator, that is, or you can say, you consider this is lambda I phi under this principle that x equal to lambda x, on this same principle. If you collect the eigenvalues, you can think of the space which is spanned by lambda 1 up to lambda n. That means, it will be spanned by e1 up to en, and the eigenvalue contribute the eigenvectors. So that is the beautiness of this, or concept of this, and take the characteristic of the eigenvalues, we can think of the solution. So in that case, what's happened? Due to this touch and the Galerkin case, in case of Galerkin, you can think about, you can represent uxt in this sense. In one dimension, you can say that I can represent this is I equal to 1 to infinity. If I consider alpha I, pi. If I take, and this pi, that is comes from here, this p1 up to pn. So in that case, you can say that this basis function derived from this Laplacian part. So once I adopt this, replacing this uxt by this values, I can get a system of equations, and this system of equation is nothing else, that is d by dt pi plus, we can lambda I, that is pi, that is equal to f. So once I get this system, we can say we can got the solution by the Picard's theorem, and this Picard's theorem, you can say we can derive it in this sense of, like, we can say that p, that is at any time t I, that you can say this is p0 at time 0. Then we can think of this case, that is some other terms are there. This is 0 to t, integration over 0 to t, e to the power minus lambda I t minus s. This is fi ds. So using the Picard's theorem, it will be confirmed about the existence of the solution. Then the story becomes that how people think about. Similarly, here you can think about the error estimates. The error, you can say, in the finite dimension, when you think about to solve this problem, ut minus Laplace equal to f, you can say this is the space. So this problem you can apply in finite space. This is the time. So this time discretion, you can apply the backward Euler method. So you can say this is un plus 1 or un forward method by t, or you can apply, this is the reliable method, un minus 1 by t del t, and this stuff you can deal with in your finite space. That is, you can say grad u in finite space. This is f in grad u, that is in the finite space. So the question is that in this context, you can see that I can derive the solution. That means I can retrieve the solutions from un minus this un, the left hand side, from the right hand side, un minus 1. So in this case, if you think about the error estimate, you can do this error estimate. You can find out u minus uh, that is less than equal to. You can say again, you can get ch square. Your uh is in your b, that b equal to, you can say h2. That you can say this norm square. So that is also fine. So someone can, that means I can adopt the similar technique in elliptic case, and you can get a similar. I can adopt the similar technique in the parabolic case. But this is give you the advantage because the same analysis you can carry forward here. But the problem comes out. People are trying to think that, because when you think about this particular issue, actually we are running out of time. But I'm not yet come to the H1 Galerkin method. So for this, you can say let's focus on the mixed finite element method. In case of mixed finite, what I'm going to do, I am trying to reduce the derivative. So as if I have Laplacian u equal to f, rather than solving the problem, what I'm going to do, I can represent this problem in this way. This is divergence of grad of u equal to f. So take grad of u equal to rho, then we can say grad of rho equal to f. So this is the way that we can split. Now you can say only one derivative will be there. So as one derivative will be there, then when you think about to transfer it to the weak formulation, so you can say this is grad u. So I have to multiply grad u here. So this is grad u equal to rho into grad u. And this side you can say grad rho. So this is the grad rho. So I have to multiply certain things that you can say. Let's go for the L2 multiplication. So you can say this is simple chi that is equal to f chi. So when I split this equation, I have to think about the different methods. That means which domain I can choose. So this is the derivative domain. You can choose that u belongs to your h10, and this is in f in L2, so you can choose u in L2. Some people thinking this is in h, some different space. So in this case, this is called your mixed finite element method. After that, they can carry forward the analysis. But in this particular case, you can say that the still LBB conditions you have to justify. That is not difficult, but difficult in the sense that means I cannot go to the Picard's concept and do the things. I have to justify this through by the LBB conditions, and that is challenging task here because I am introducing new term, new things are there, some new analysis will be there. So the advantage what I can get, that I can get from this part here when I go for the particularly parabolic problem. Here you can see that we have the term u minus uh square. One more term you can say, because I have the first term, that is you can see that here one term that gives me u, this term gives me grad u. So for that case, we have some more result that is called h square grad of u minus uh. That is also I'm getting. But the question is that in this process, you can say, you could think about, so this is h only. So you can, when you try to think of this case, h grad u minus uh, that is less than 2ch square u in h2, you can see that I'm losing some order. So for that, people are thinking about to apply this in using of mixed finite element method, because in the mixed finite element method, they will be retrieve the order here, and when they will be imposed here, they will be get the result. That is the story about the mixed finite element method. Now come to the message is that, or matter is that, when I think about this mixed finite element method and I'm using the finite element space, usually what exactly happening in case of finite element space. So last time Sangeeta was trying to explain something P2, P1, some stuff up like that. How this finite element space look like, we can see in this way. That when you try to think about the finite element space, we can represent it that my domain is, let's say, h10 intersection h2. No problem. I'm choosing the space. This is the subset of this. Or you can choose this is the space directly. When I'm choosing the finite space, this is BH. That's the subset of B. But if you think about the members, this BH, how it look like? We can choose BH belongs to C0, that the continuous function, and BH upon a interval I, or you can say upon an element or any triangle TR. This is belongs to PK upon the triangle. So, and here you can say that this PK has the direct impact on the solution. So if I write down the same form in other way, I can say u minus uh in parabolic sense, this square plus h grad u minus uh. You can see what exactly happened. This square, if I choose, okay, this is outside. So I'll stop it. I'll just give the information that how we can deal with the case. So we can say, if you think about h into grad u minus uh, this square, you can say this is, I can write in another way, that is ch to the power r. That's what's happening. So we can say ch to the power r. This is v in hr. So this r, you can say this R is less than equal to K. So that is the direct link with this polynomial, this Pk. That means if I am looking for order 2, I have to take P2 maximum. If you take this polynomial degree 3 or more, that is also give you P2 maximum P2. So the difficulty is that when I take higher polynomial, the computations are difficult. That means the computations will be hectic, or you can say expensive. So for that case, in 1996, Professor Pany, fortunately is my uncle, in 1996, he was started working on H1 Galerkin method. So what is the advantage in H1 Galerkin method? In this method, you can see that when we're trying to solve this problem, particularly using of, you can say, this case, when we're trying to transfer this information, fortunately H1 Galerkin is still based on, or you can get lot of material from parabolic and hyperbolic. They are not succeed for the elliptic case. So what they did in this lesson, that means they pick the problem in this way, that is a general problem. They choose, if my equation is Pt minus Apx, whole upon x plus Bpx. So it is the oil reservoir problem, you can say Cp. If this is equal to F, if this is equal to F, in this problem, you can say how you can do. He split this equation to two parts. That two part is that he was taking Px equal to alpha x u, that he compromise the derivative by u, alpha x u, and then we can, and the rest of the term, this equation can be transferred to ut alpha of ut plus ux equal to beta u plus Cp minus F. In that context, what exactly happened? When you are trying to go for the variational formulation, you take this way. So this is Px dx. He was taking the derivative space equal to alpha. This side is u. Then multiply with the Vx. So this is the derivative space. He choose this P in H10, and this part alpha ut. What we are taking supposed to in you can say L2, in place of L2, you take it is in, so you can say this is Wx equal to beta u Wx plus Cp Wx minus F Wx. So what is the interesting thing is that you are choosing this W in H1. So what is the advantage you can get here? When you choose in place of L2, when you choose H1, we can see that when you think about the error estimate U minus UH, if you think about the error estimate, because you can take U minus UH and UX minus UXH, because you are separate the things. So when you go for the error estimate, we got very interesting result. That result said that this result in 1, which is the problem actually. In the first space, you can see that in H1, he gave this result is that CH to the power minimum over K plus 1R. That means this say that if I'm looking for the H2, that this K, if it will be 1, we can get the solution. That means if for two space H10 and H, here if I choose my polynomial is Pk, that means you can say P1, we got the H2 solution. So that is the requirement, that with a linear polynomial we can get a better result. That's why this H1 Galerkin is used in a fashionable manner. Later on, lot of people contribute lot of work in H1 Galerkin method. The advantage you can say that with minimum computation cost, you can get a better result. So I think I should conclude my result. Any question? Yeah. Yeah, anyway, we are belongs to one. Our family members are there. There is no problem. If you have any questions, any things, you can come to my cabin. Yes, sure. Yeah. Hmm. Laplace transformation. Laplace sum operator, yes. Laplace operator, yes. What the question? No, it is not transformation. It is operator. It is nothing else. It is uxx plus uyy. Yeah, similarly you can follow. There is no problem. That means the just thing is that this is I am represented Cartesian form. If you go for cylindrical coordinate, this is written r theta form, nothing else. Yeah, issues are there. They are solved in different directions. Like if you have singularities, when you think about if you think about a cylinder and we're trying to triangulate it, I can triangulate it. But let's say some particular point the singularity will be there. In finite element analysis, what exactly happens where I can get the singularity particularly? If the angle, this angle will be like you can say the domain or you can say the domain, any place you could find out this angle is exceed more than 270 or 270, 207 I think so, or some exact fixed quantity there. After that, in this kernel, you have the singularity. Basically, you can understood in this sense. Suppose in the flowing pipe, there is no singularity. But if I bend the pipe, even there is no singularity. But if I bend very more way, that means this point I can get the singularity. So when I adopt the finite element method, you can say we have the singularity. I'm not saying about it. Even I cannot rectify. But once I got the singularity, let's say singularity on this point. Let's say singularity on this point. Because I have the grid will be given information. So if the singularity on this point, what I'm going to do, I have to take care about the grid. Okay. So you can see that last before Dhananjay was presenting, I was saying that because there is a job at a particular point. So that can be improved by using adaptive technique. That is a way that you can improve the singularity, or you can try to avoid this interval point. So to avoid this point, you can get a better solution rather than exact point where the singularity occurs. I will not choose that is the grid point. I will choose the grid point closer to that, so I can improve the solution. That I can apply the continuity limit sets to get the result there. Okay, thank you very much. Any other questions? So I will stop here.
Yeah, I think no more questions are there. So, Dr. Ambit, thank you so much. Within a short time, you could prepare yourself for this nice and presentable talk. This very the presentation is also nice. And thank you so much. Now I request our Dr. Abhijit so to formally offer the vote of thanks to our dear Dr. Ambit.
Yeah, ma'am, I have a proposal.
Yeah.
That today discuss a lot of stuff at one place. So if anytime we have like this kind of stuff happen that we don't get the speaker at a short span of time, so I can continue. That means I make it to small segments. We have to talk about finite element and mixed finite element. Like in this segment, I'll continue. If everyone like it, that's the question.
Thank you so much. Thank you so much.
Okay.
See to it. Future, obviously. So thank you, everyone. Thank you, Dr. Ambit. Thank you, Dr. Let's meet up. Yeah.